All right. There it is. All right. Tonight's topic is the COMPACtenna. Dr. Jack Nilsson N8NDL, excuse me, is the inventor of a revolutionary antenna science and technology. His various designs are used by many agencies, including the United States Secret Service, Washington, DC, Homeland Security, and the Cleveland Clinic Mobile Stroke Ambulance. So Dr. Jack, why don't you go ahead, and the floor is yours.
Well, thank you very much, Ed. I want to, before I go to the PowerPoint, to extend my thanks to Conejo Valley Amateur Radio Club of California, including Ed Zimmerman, President, Brad, Phil, Martin, all on the board. Thanks so much for your efforts to put this together. Also, some guests that are signed on from around the country, including Harold Wong that we talked about a little earlier. Harold KM6IVE of Los Angeles has done a couple of really well-made videos driving around and through tunnels of Los Angeles, showing one of the characteristics of this science and technology, being able to hold the signal in highly obstructed areas. And also Stephen already, KC3 DSO, thanks for coming. Anybody else? There's multiple screens now with so many here. It's great to see all of you, all the members of the club that were able to come, as well as anybody that I've missed. I apologize, because there are now a couple of screens at least, if not 3. So, all right, I'll go ahead. I hope that you find this presentation enriching. It is a development off of prior presentations, so there's more information here, and hopefully somewhat entertaining as well as enriching. So I'll go ahead and share screen. And we'll start from the beginning. If anybody can chime in to see if that is full screen now, if you can see it.
Yes, we can see it.
Excellent. Thank you so much. Thumbs up, Brad, as well. Excellent. All right. Well, so I'm Dr. Jack Nilsson with a varied education that started in physics and mathematics. And then I moved into the practice of medicine. And then after some time, as a result of really all the HMOs and the managed care type of things, I went back into the area of physics and mathematics in the inventive nature with antennas, and that was about 20 years ago, and since then developed a number of revolutionary antenna technologies and patented technologies. So today we're going to talk about this one. This is COMPACtenna.com. Small, high-performance antennas, which in and of itself is kind of an oxymoron, as we know, because when you use standard antenna technology and you start shortening the antennas, all kinds of terrible things happen, right? You know, the efficiency goes down, the linear average gain, the bandwidth, I mean, all kinds of things. But it's so important. It's so important because, you know, we have parking garages, we have our own garage, we have drive-throughs, you know, and all of us have taken, you know, larger antennas, you know, the old idea that the bigger the antenna, the greater the gain, the greater the performance. Sometimes, a lot of times not the case, though. We'll talk about that. But nevertheless, and, you know, we would either have a magnet mount and pull it off and put it in, jump out of the car, you know, regardless of the weather, or we would use foldovers or whatever we had to do, you know. So this is a different solution. This is where the antenna itself is very small. And oh, by the way, there's also no tuning of the antenna structure itself. And it's just very convenient. So the idea is, well, can you do this and still get reasonable performance? Yeah, you can, but you have to do it in a little different way. Well, a very different way, really. So what's it about? What kind of antennas? Well, they're for ham radio, for CB, for scanner, police scanner, land mobile radio, GMRS. Let's see, this is actually getting in the way of my view of the presentation. And my arrow, let's see what I can do here to move this around a little bit. Ah, that's good. I can move that like that. That's a good thing. Okay, and GMRS and also shortwave. Actually, the GMRS is part of the land mobile radio model. Specifically to ham radio, there's 2 meters, 220, 440, and 20 meters. Okay, so here you see, actually, this is my present vehicle, and we have one antenna here. Notice it's all the way over there at the corner, and this one over here all the way over at the corner. Yeah, there's a reason for that. You know, through so many years using regular antennas, you know, the goal or the direction was always to get into the middle of the vehicle, the middle of the roof, right, and get the largest ground plane in all directions, and then more and more vehicles would have the sunroofs and the moonroofs and all of this, so you really weren't getting that benefit. But you know, if you didn't want to go into the middle of the roof, sometimes you'd have a hard time getting the antenna to tune up well. Well, so this actually provides you the option, which is great. There are 4 upper corners of the vehicle, and sometimes even the lower corners work well. But you know, particularly it's recommended one of the top 4 corners. However you do that, and we'll talk about why that is. Particularly for SWR at Vhf. This is the antenna on an NMO ground plane adapter kit. You know, there are various adapter kits out there, but none of them are optimized for both SWR and pattern on all the different frequency bands, you know, of Vhf and Uhf. So I decided to design one that would do that. So you know, with the increasing popularity, and thank you, of these antennas on the vehicle, it really makes for a very, very nice base station antenna, either on the roof or in the attic, because it has obstruction penetrating capabilities. We'll talk about that. But even outside or in the backyard, you know, on a mast, it's hardly visible. It looks like a vent pipe, so it's really good. This is the 20-inch antenna. So again, the Vhf, Uhf, they come in 7.5-inch and 9-inch, and the 20 meter, the CB version, the shortwave version, they're only 20 inches tall. This is on a specific counterpoise designed for it. We'll talk about later, sitting out in the backyard. I mean, nobody's going to see that, or for POTA operations or whatnot. All right. So, oh, it looked like it jumped. Okay, very good. All right. What are the conveniences of small size? Well, first of all, no tuning of the antenna structure. That's great. Makes it a lot easier. Okay, but you do need to get into the corner for the optimum SWR. Even the 20-inch HF antenna, all right, the CB or the 20 meter, if it's mounted on a vehicle, then near the corner, at the corner of the vehicle is very, very helpful for the SWR. Sometimes the HF works well anywhere on the vehicle, but many times at the corner. Has a lot to do with impedance characteristics we'll talk about. This technology could, some people would ask, theoretically be designed to mount in the middle of the vehicle, but then again, it wouldn't be as good in the corners, and there are more corners than the middle. But you would actually decrease the performance if it were designed specifically to go in the middle. So at the corners, you get the downward counterpoise. It does help. I'm jumping forward a little bit. Sorry about that, but I thought it was good to get that out of the way. So there's vehicle and there's home. What's good about a small antenna? Well, allowing passages into the garages and all these kind of things. In the home, it's obvious. More HOAs, condos, apartments, homes, people just don't want an unsightly antenna up there, but they would like to have reasonable performance. And if possible, really good performance. And that's what this provides. So so I've kind of mentioned this already. At the 20-inch antenna, I mentioned the backyard, patio, shed, floor of the house, closet, attic, all of these kind of places. POTA is increasingly popular. Campgrounds, field emergency deployment, to have a small antenna that is easily deployed. That's the other thing. Small, no tuning, easily deployed. The counterpoise, as you saw a glimpse of there for a moment, you know, what good is a small antenna if you need whatever, 90 feet radials and 26 of them in all directions or more, right? This is designed where the HF even works with this technology with a small counterpoise. So small antenna with small counterpoise. Just a lead into the way I did that was totally different. By using sheeting, both in the antenna, but also in the counterpoise actually couples capacitively to the planet Earth, to the groundwater of Earth, okay? And even if it's in the attic. And this way, you get a substantial counterpoise that is necessary. They're not wires, it's sheeting, always sheeting. All right. Quick outline of what we're going to do here, and I will keep an eye on our time because I know that too long is not good. So if I brush over some things and you want to ask more about it later, go ahead. And you know, I can't do an entire dissertation on science technology, both of present understanding, you know, of standard understanding and this, you know, so again, you can always go back and look at the YouTube on that, and thanks for bringing it to YouTube. So there's two parts to this presentation: the science and technology and the models, okay? First and second, essentially. So the new design, we talked about this. Now, how did I do it? It's with what's called the magnetic field resonator. You know, I've used some terms here because I needed to coin some terms because they don't exist, to try to describe what's going on. And all of this occurs in visionary thinking, typically as I'm awakening, and it all comes into place. But then it takes years in order to perfect it and bring it to fruition. But it is what it is. And how is that done? Well, it's a sensitive keyboard here. It's done with what I call an extended flat monofiller Tesla-like coil. Okay, that hasn't been done before, strangely. Certainly, we have antennas that are, you know, say a quarter wave that's a wire, or if you want more broadbanded characteristics, a thicker wire, or you can use a sheet. And then there was even an IEEE article that I noted after I patented this that takes the sheet and then even rolls the sheet, but it's still a quarter wave high. Okay, it's not a quarter of a quarter wave high. You know, it's not very short. It's entirely different. The characteristics of this are surprising when done properly. The matching circuit, this is so important, is intrinsic to the antenna construct, okay? The matching circuit is intrinsic. Reducing the matching circuit losses, that's so important. How are you going to make a small antenna? You know, if you've got all these losses in the matching circuit, no, there is no separate base, you know, capacitor, inductor. It's all within the construct. You'll see that in a moment. Active component of the electromagnetic field production, yes. So not only is the matching circuit part of the antenna construct, it's an active component properly to enhance the overall electromagnetic field generation. Okay, and because it's made with sheeting, it can be broadband, it can be multiband. There are some added components to the structure, but that's basically it. So that's the basics. Where did my arrow go? There it is. Then it also does something else. The flutter reduction. You know, most of our communication is not line of sight. 99% of it is non-line of sight. So if you develop this matching system intrinsic to the antenna that is also an active component of the EM field generation in the far field, and then near field to far field, we'll explain that. And then You also do some out of phasing, so you develop an elliptical polarization. Well, then you're going to capture a lot of the dramatic signal drops that you have because of shifts in polarization in the multipath environment. Oh, that is a long sentence, but that's what it does. So, I mean, just like a circularly polarized, any elliptically polarized antenna will do that. So, to some degree, and that's what it does in analog, and especially in digital. Because you get those dramatic intermittent losses. Not only do you get irritating flutter of the voice, but you wind up getting bit error rate. You start getting frame rate errors. You get drop in throughput, even connectivity. So everything that it does analog, it does even more so in digital. And what else? It does another thing. Really, it's different. Noise reduction. You'll see some testimonials on that. Because of the balance of the magnetic and electric fields in the near field, and because of the polarization diversity, you get noise reduction of the vertically polarized electric field noise that you get from, man-made noise. We all know about the magnetic loop, decreases it because it's like almost entirely magnetic field in the near field. Well, if you have an antenna that does all of this, but has a predominance or a predilection for the magnetic field, you get an even better noise reduction. You'll see that somebody volunteered that, putting it on their Tesla vehicle, and the noise diminished. Interesting. Lastly, diverse pattern. Satellite communication. Omnidirectional monopole antennas typically do what? Going upwards. It's gone, right? Whether it's a quarter wave, a 5/8 wave, a collinear antenna, you've got almost nothing above. You have an added field above. It's a very broad elevation coordinate pattern. So it's a really favorite for satellite communications, mobile and base communications. I know it's to some of you, it's like, really? All of that? Is that even possible? Well, you'll see when you see the construct, how that's done. And we really already talked about this already. All right, next. So when you look at the logo, and anytime interrupt me, Ed, or anyone if need be, but the logo pretty much explains it. See here, you have the satellite communication, broad pattern, extra lobes going upwards. Here you have the diverse electromagnetic fields, near field to far field. It's all in the logo, actually. So already discussed this, discussed that, and discussed this. So I'll just take a moment on it. That's the patent number. That's basically it. 1, 2, 3. And that's, of course, different than any of your standard antennas, right? We'll see how. But there's a lot there, right? Almost started doing a dissertation on antenna performance. So I'm just going to brush over it. But, when we look at antenna performance, we jump to SWR. We got those nanos out there, nano VNAs and SWR meters and all of that. People jump to SWR. Yeah, that's part of that's part of the equation. Sure it is. And gain, yeah, that's part of the equation, but there's a whole lot more than that, everybody, when it comes to, and some of you know this already, when it comes to antenna performance. SWR, reflected power, you know what that is. Antenna efficiency, what is that? By definition, it's the ratio of the power radiated by the antenna to the power supplied to the antenna. What does that mean? Well, you can put a certain number of watts out to your antenna, but how much of it is coming out in the airways? All right, that's antenna efficiency. All right, so that's an important thing. You'd love to have 100%. Very few antennas actually have 100%. A perfect dipole, a perfect dish antenna with a perfect LNA feed. But many antennas that operate very well are actually in the 50 to 60% category. And some are as small as 5%. When I developed antennas for Amphenol, for example, for General Motors and Tesla vehicles and these kind of things, these shark fin antennas, you cram all that antenna technology into a little shark fin, including an AM radio antenna, you're down to really low efficiency. And if you can increase something from 6% to 8%, well, you've just Wow, that's almost a miracle. You know, so so efficiency is important. All right. Losses. All right. So you have an antenna construct that potentially would release the energy and give you a reasonable antenna efficiency, but there are other elements of the antenna construct that can impede you even further. All right, the element dimensions and construct itself, how large the element is, what the construct is. Larson, for example, came up with the cool rod, a triple layer thing, just to reduce slightly, or but substantially. It's hard to use both words at the same time. Of heat production to help on that. The dielectric. What is the dielectric? The dielectric is when you have a coil and it isn't just air between each layer of the coil. You have a dielectric that can cause loss. Oh, there's all different types of dielectrics that can be used. The substrate, like a patch antenna, patch antenna, then the substrate down to the ground plane. All different types of characteristics of substrates, and they can create loss. The radome itself, the covering of the antenna, so much is going into the study of the radomes of the antenna. They not only can change the impedance, they can create loss, they change the elevation coordinate pattern in an omnidirectional antenna, et cetera, et cetera. Okay, the matching circuit, multiple losses. How? Well, the element itself, the dielectric, the field grounding, the grounding of the field. If the matching circuit is near the ground plane, right? Not only do you have the loss, relative heat loss and whatnot relative to the matching circuit, but the field itself can ground out. Okay, and I'm talking fast. Is this going all right? Yes? Okay, I get a nod also from Norm. Okay. You play it back and slow it down, maybe. Sorry about that. I had this extra coffee because it's late here, Eastern Standard Time. Intended field cancellation. Intended field. Remember I talked about the magnetic field resonator, right? And that creates its field, but then you have the primary intentional part of the field. Well, if you create cancellation between the matching circuit field and the intended field, well, that's not good, is it? So that has to be done right as well. Okay. All right. Talked about that. Matching system, but yeah. Okay. Gain. All right. Gain. Yeah, gain is important, but so is pattern, right? What's the typical example? Take very simple example. We're driving along in the car. What are we going to use? We're going to use a quarter wave? We're going to use a 5/8 wave, a collinear antenna, a half wave? I used to use a half wave because it was kind of in the middle. Why? Because when you're hilltopping, you still get some reasonable gain, and you're essentially line of sight or near line of sight. But then when you're down in the valley, you don't want too much gain. You put I used to have a 7-foot 2-meter antenna collinear on there with guy wires, and the signal was just slamming into the side of the hill. It wasn't doing any good. It was that you're actually better with the quarter wave. So all of this adds up to why my spec sheets say that the performance is greater than anticipated or predicted based on gain alone. We can use a new term that's being used called mean equivalent gain. It takes all of these characteristics into consideration and throws that in there. Okay, so gain, yeah, but pattern. So okay. Yeah, I already explained that. A signal capture. All right, I talked about that as well, so I don't need to do that again. Time constraints. Spatial diversity. Well, actually, because in the multipath environment, you have additions and cancellations, and we all know this. We come to a stoplight, the signal's gone, we creep forward a couple feet, voila, it's back again, right? We got into a hotspot. We got into a positive reinforcement, positive cancellation. That's horizontal. It also occurs in the vertical. So sometimes the higher gain antenna, being that it's very long, you will also have vertical spatial diversity, and that can benefit you. All right. Polarization diversity I talked about already. Noise reduction. All right, these are all the, well, there's many more than this, all these things that cause noise. You know, it used to be the power lines we usually focus on, right? And, you know, arcing transformers up on the poles. Now, a lot of times it's inside your own house. So take the 20-meter antenna that's 20 inches. Yeah, it created a short counterpoise for it. You can use it in the attic, I do. But if you put it out in the backyard, many times you get much, you know, less noise, because, you know, noise from within your own house with all these things. Now, of course, I've got RF beads everywhere and grounding and all of that kind of thing, but just saying, you know, sometimes it's beneficial to have a very small antenna outside that the neighbors don't complain about, because you immediately decrease the amount of noise. Hive can help you a little with local communication. But if you're doing mainly ionosphere propagation, you know, it doesn't make much difference. Pattern polarization, we talked about that near field. Okay, we'll get to that a little bit more. All right, so what has been done in the past? Let's see how the time is. Oh, that's not too bad. All right, standard technologies for matching. Okay, a lot of you are familiar with much of this here. Basically, you know, these are the various types of things that are done: shunt, inductance, capacitance. You know, you have a shorter antenna. The high voltage point is near the ground plane. You get a decreased resistance. You need to improve on that. How do you do that? These are the kind of ways you do that. Again, I'm not going to. I'm going to brush over, not to show ignorance, but just for the sake of time, and the sake that a lot of you already know this already. There's a variety of things that can be done. This has everything, including the kitchen sink, thrown in there in order to match it up, and that's the way things are done. Let me move this out of the way here. Fortunately, you can't see it. Oh, it went down there. That's good. So here we have the ARRL handbook. You know, things are more complex than we think when it comes to monopole antenna. There's actually you know, LC, 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 LC all the way up, right? We've seen that before, haven't we? Right? Like in the transmission line, the equivalent circuit is LC, 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 LC. So, well, of course, what is an antenna of this nature? It's a transmission line that's split. So you get the same kind of thing going on. All right, let me see if I can move this thing completely out of the way. That would be good. Whoops. No, that didn't work. All right, I just hit it. That's much better. Okay, so and here we have equivalent circuit of the transmission line. But what happens when we do all of these things? We get decreased bandwidth, decreased gain, matching circuit inefficiencies. I've already mentioned that. All of those things can occur. Hey, some less than others, you know, thicker wire, bigger coil, air coil rather than the loss I talked about with the dielectric. You know, all of those things can help. But that's the way things have been done. Is there another way? Yes, this is the other way. All right, so here we have a stem, and then we have the foil of metal that is wrapped on itself. An extended flat monofiller Tesla-like coil, creating magnetic fields that shift as you continue outward and then out to the electric field. But notice also that we have the magnetic field here in the high current area, but then, and this is important, out of phase. We have vertically polarized magnetic fields here, out of phase with this one. Now this is in the near field. But the near field, and we're going to show this a little bit later, and the far field are very related. And what's generated in the near field then supplants to the far field. So we have diverse electromagnetic fields, and as well, these are actually not entirely vertical; they're slant as they move around. So we have out of phase slant polarizations, both magnetic as well as electric field. That's how you get the reduction of flutter and the greater reliable range. All right. Now again, if you have a very high gain long antenna and your line of sight and you're at the hilltop, hey, that's really going to benefit you. There's only so much you can do. But 99% of the rest of the time, this gives surprising results. Now, why is the matching working on this? All right, when we look at a standard helical coil up here to the left, I hope you can see that arrow. I made it as large as I could. Of course, we have inductance, but we have intertwined capacitance as well, also down to the ground plane. But it's not a lot. Okay, this is the essential circuit equivalent of it. It's not a lot. COMPACtenna is much different. For the same length, you get in a monofilament spiral Tesla-like coil, you get greater inductance, and also you get greater intertwined capacitance. It's kind of obvious. And they're in parallel. They're in parallel. This is helping you with your impedance mismatch. This is the matching circuit within the antenna itself. All right. So you get greater than expected both electric and magnetic field components, relative propensity for the magnetic, we'll talk a little bit more about that, and overall superior for size electromagnetic field with the beneficial elliptic polarization and all of that we talked about. Okay, that's redundant. All right. I'm going to pause for a moment. If nothing to be said, I'll move on. Before we get to the models, let's dig a little deeper. This is a new component of the presentation from the circuit properties, the RLC, resistance, inductance, and capacitance, and the macro, I call it EM signal field that we've just talked about, to the quantum level. I wanted to do some of this, all right, because this is how the vision comes about. It comes about on the quantum level, and then translates to everything that actually has taken me a while in order to explain. So you all know Einstein and Niels Bohr. This is a historic picture where the two of them are talking, and Niels Bohr said that varied in the equations is this entangled characteristic, this quantum entanglement, because Einstein was all about the maximum speed being the speed of light, and all properties through that. But mixed in here is what Einstein called the spooky action, when Niels Bohr said, yeah, well, it would appear that there's instantaneous interaction between things at a distance, often a very great distance. And that cannot be explained with the special or the general theory of relativity, where space-time has the speed of light as a limiting factor. Does this play any role in antennas? That's where I wanted to bring this to your attention. It absolutely does. All right, now I'm going to brush on this. This is a drawing I came up with to just overview it, okay? We have the near field, we have the far field, and we have what's in between, which is a mix of the near and the far field, okay? And in the far field, of course, we have the photon, which is a gauge boson. I won't go into all of the different types, but it's a gauge boson. And it's at approximately the speed of light. Why do I say approximate? Because it's going through a medium, right? So in the electromagnetic far field, we have photons moving at approximately the speed of light, all right? In the near field, we have something entirely different. Think Niels Bohr near field, quantum entanglement, immediacy of interaction, and think of far field speed of light, all right? Now, what is the definition of the far field, where it's 1/2 d squared over the wavelength? And so what that means is, for example, if you have a dipole antenna that's a half wavelength, well, 1/2 wavelength d squared is 1/4 wavelength squared divided by the wavelength. 1/4 wavelength times 2 is a half a wavelength. So at about a half a wavelength, you have at least the beginning, or you have your near field. Now, if you have a collinear antenna, or your far field, you have your collinear antenna where d is much longer. Your far field with the collinear antenna, where you get the summation, essentially, of the various fields of the components adding up in a high gain tight elevation coordinate pattern, well, then that far field is distinctly greater than a half wavelength. It can be even more than 2 wavelengths away, okay, based on that formula. So near field, far field. Again, I'm just giving summary ideas here. So in your, now let's look at how that applies. We talked about a dipole, which is here. How does that apply to a shortened monopole? Here's your matching circuit at the bottom in this case. I know it can be in the middle or all the way through, but in this case, we have the magnetic loop and then we have the COMPACtenna. How does quantum physics, how does immediacy of interaction, quantum entanglement, and then the far field relate to all of this? Well, this is how it relates. In a full-size dipole, you have, let's call it a substantial electric field, right? Substantial electric field, high voltage points at the tips, the high current magnetic field here. You have a substantial magnetic and electric field, and they, in the near field, they contribute to the end result of the far field, which is electromagnetic wave propagation at roughly the speed of light, okay? Well, what happens with the others? Shortened monopole, what happens there? We have reduced strength. Well, yeah, you sure do. You have both the electric and the magnetic, definitely the electric field, definitely the magnetic field, and a predominance of the electric near field. Not very good when it comes to electric noise, you know, electric field noise, noise generators that we talked about that are primarily vertically polarized and electric field. Not good. What about the magnetic loop? Yeah, well, it may have very low efficiency, but so reduced strength. Of course, if you put a preamp on it and as a receive use, it's very good, or a very expensive one that can take some wattage. But the predominance is in the magnetic field. Okay, so here we have reduced electric and a magnetic field. Here, every reduced electric field, almost none in the near field. What about the COMPACtenna? You know, and then of course, what ends up in the far field again is contributed by these two. What about the COMPACtenna? This is neat. The electric field strength is reduced, but it's distinctly greater than expected for size, based on what we've talked about already. What about the magnetic field? It's actually a propensity for it, and its strength is high. So when you have substantial still electric and magnetic near field components that summate, if you will, or contribute, as you will, to the electromagnetic far field of the gauge bosons traveling, the photons at the speed of light, well, then you get a surprising overall strength in the electromagnetic field, much more than you would think, okay? And then, of course, I talked about the diverse electromagnetic fields reduces signal flutter reduction. This is another diagram of the near field and the far field, basically saying the same kind of thing here. All right, let's move on. So what does that do in a sense? Well, all right, let's say you have your higher gain antenna on your vehicle. You're going to have peaks right here, okay, in the red. Definitely stronger than the shortened COMPACtenna. Definitely less. You can see that. All right. But when you have the 20 to 30 dB drops due to polarization or spatial diversity drops in the multipath environment with the standard technology, look what happens. You smooth those out. You smooth it out with the COMPACtenna. So, you know, whenever propagation analysis programs are done and you want to have at least a 15 dB fade margin in order to take care of these kind of things, hey, you really don't need that with COMPACtenna. Now, eventually, if you shift all of this way down, so only the very few signals are making it above the minimum, hey, you need your gain. But in the majority of your moderate far ranges, you definitely would get flutter reduction based on this concept. And then, of course, the noise reduction because of the magnetic near field. To snake oil, you know, 20 years ago when I, you know, proposed a number of patents on single feed electromagnetic diversity, spatial and polarization diversity, you know, a few embraced it, many thought it was snake oil. Here I am doing this one now, and of course, you know, you get your naysayers. Now it's been out for about 5 years. By the way, the antennas around 5 years ago didn't have any labeling underneath, because there was only one model, the tri-band. It was right around, in the construct of it, was right around the time of prototyping. All right, so it was rather crude. Things have developed quite a bit since, and you'll see that in a little bit. So let me stop sharing and show you one of these antennas with this question. Stop share. All right, can you see me now? Yes?
Yes.
Yes, okay. All right, so here we have it. All right, here we go. Can you see the whole antenna?
Yes, we can.
All right, you see that? All right, let's bring it up a little closer. Can somebody read that?
We are now with the 20% more snake oil.
Absolutely. There you go. Oh, that's the wrong antenna. Oh, I'm sorry. That's the. Oh, here it is. This is the real deal. Here's the COMPACtenna. All right. So this happens to be the 2M440 Plus that was talked about before. How do you know it's the plus? Because you look at the bottom. And right there is the plus. NMO connector, a plus. So if it's the land mobile radio version, it's an L. If it's the dual band 2M440 7.5 inch, it's 1.5 inches shorter than this one, then it's a D for dual, a T for tri-band. That's how you know. All right. So hope you enjoyed that. All right, let's go back to share screen. All right, there we go. All right, and from current slide, let's see. Oh, I see. I have to go back. Oh, there we go. All right. All right. So what do people say about it? All right, let's start with the Vhf and Uhf. Yes, as far as is it real? Bob Grove, an excellent individual, known by many as an expert in spectrum monitor. A couple years ago, the prediction of signal flutter reduction was true as well. When annoying flutter interrupted reception of weak signals on the WIP, reception was much smoother with COMPACtenna. Anybody else? Yeah, there's a lot. I'm just picking a handful. Here's on eham.net, Scott Roberts, KV3 CBC, talking about the tri-band 7.5 inch. The noise floor was reduced by approximately 3 dB. The noise floor was reduced by approximately 3 dB. Remember we talked about the magnetic field propensity? And the signals were more evenly distributed. Signals that were close to the noise floor, where you get the drops in the others with the multipath environment, and this applies also to ionosphere propagation polarization shifts, not just in the VHF, UHF land mobile world, were observed to have increased by 3 to 6 dB, and stronger signals were slightly attenuated. Absolutely. This shows you that this was an honest testimonial, one of high integrity, because the stronger signals were slightly attenuated, but it didn't matter because you still had enough signal. Again, unless you're mountaintopping. The result is that there was minimal fading, or if you're very far out with very near line of sight, minimal fading and capability to hear signals that I could not use in the other manufacturer's antenna. So yeah, there are naysayers anymore, but here's one, W4PIG. He says, I have the tri-band version. I've had it going on 3 years. Excellent antenna. I had my doubts, but boy, was I wrong. Yeah, thank you. All right, well, there's a lot of good reviews. Here specifically on the near field, when we talk about near field, we often talk about magnetic loops. We talk about HF antennas, right? Okay, but you know what? This is applicable also to the near field of the VHF, UHF communication world, especially when we have these electric vehicles, right? You know, a Tesla vehicle, for example, doesn't have an AM radio in it. Will be completely blocked out. Could you create enough of a noise filter? Yeah, it'd be huge and expensive. So in this case, On my Tesla vehicle, I've been testing various antennas, including long, high-gain VHF, UHF one. There was a noise problem when driving as well as when parked in the on mode. That's important. All the electric capabilities. Even with the repeater only 8 miles from my location, the COMPACtenna does not have that issue. That's due to the strong immediacy of interaction, Niels Bohr, near field, magnetic and electric field with a propensity for the magnetic, and then a strong far electromagnetic field. How strong? Sometimes it's not just the flutter reduction in the non-line of sight, it's even surprising results, especially on the 9-inch 2M440 plus, the premium 2M440 antenna. Don't get me wrong, the 7.5-inch versions are great, okay? But if you want the premium, the 9-inch. Full scale signal at 25 miles away, the video is on the homepage. How I'm doing for time. Okay. Jeff, what are people saying about that? You've seen this picture. Here's the same thing in an attic. I'll describe that a little bit more. Here it is on a vehicle. Officially recommend the 20-inch antennas for vehicles not moving, you know, like in a park, POTA, campground, whatever. Users are reporting that they are having success with vehicles in motion, indicating that there are some very strong, sturdy mounts out there available that do a fine job with the wind load of this 20-inch antenna. All right. What are they finding? This is a report from a major defense contractor, chooses to be unnamed. But what they were so surprised about was that they took, this was a 20 meters, a full-size monopole, versus the 20-inch COMPACtenna. And of course, the peaks were higher with the full-size monopole. Of course they were, 14 versus 7, 22 versus 13. But when they got below 10 dB microvolt, they noticed something, gave me a call and said, this is very interesting. See, this is 1.5 dB, virtually unusable, 3 dB. See the waveform? 8 dB, 10 dB, 9, 9, 7, 8. Now look at this. When you go even much lower, right near the noise floor, like I've talked about, right, with the ionosphere propagation, or even, depending on the circumstances of the topography and whatnot, multipath, even from the planet, or man-made structures, this is almost gone, a little bit more, almost gone, definitely there, almost gone, definitely there. Okay, so peak signals were a little less, but low signal strengths are mitigated. All right. On my website, near the top, there's a really nice video done by Elcara of Kentucky on using the 20-inch antenna. Both they did activations from the ground as well as from their vehicle. This is a review. It's not just a gimmick. It took the CB antenna, put it on the ground plane. By the way, what this is just a metal sheet from your home improvement store, 3x4 foot sheet. You can use a couple of smaller sheets. They sell those too and overlap them. And then there's an 8-foot piece of just standard aluminum foil off the end, and then the antenna at the opposite corner. And this whole thing creates capacitive coupling to planet Earth, to the groundwater. Okay. And he had great success with it with his daughter, using standard CBs, President Mobile, and no extra power, and got a few miles out, said he could go further, but his daughter got tired. It's real. All right, the last part, we're going to talk about the models and then questions and answers. I'm sure there'll be some. Just don't ask me too much about that one with the snake oil in it. I don't know a lot about it. You can see it came from somewhere else. All right, enough of that. All right, so COMPACtenna models. There's VHF, UHF. There's a base station adapter that we talked about, the ideal, and then the HF. Really talked about these already. Not too much about the land mobile radio. The desire was to use this technology for land mobile radio because, there are a lot of radios out there by Motorola, Harris, etc., multiband. And what antenna do you use? And a number of studies were done actually using the Scan 3 before the LMR1 came out, which is quality tuned for the land mobile radio community. And they found great success in comparison with other antennas. So it was developed for land mobile radio as well. HF UHF, this is the dual band, 7.5 inch, 2 meter 440. What can I say? For 7.5 inch antenna, I think you'll not only be surprised, you'll even be amazed. It really does a nice job and gets you where you need to be without the nuisance and the unsightliness. It's a pleaser to the family. The tri-band was actually developed first. It has an extra magnetic field resonator in it for the 220 band. The dual band was developed afterwards to save some money for the cost-conscious ham radio operator. The 2M440 Plus I mentioned has all the high performance of the 7.5 inch model, an extra dB and a half, 9 inches tall. If you can fit into your garage and whatever with it, great. Okay. All right. This is the land mobile radio. So what is it going to be? Well, obviously it's going to be tuned for these frequencies: 36 to 174, 378 to 512, all the federal government, police, fire, sheriff, emergency medical, state highway patrol, Homeland Security, U.S. federal military, also GMRS and MERS, by the way. Very, very sharply tuned nicely for 150 to 162, which is very important for land mobile radio communication. So all of these radios, Motorola, L3 Harris, If Johnson, Raytheon, Tate, both monoband as well as multi-band radios, can be used on the compact counterpoise as a base station repeater, such as on smaller stations. When your installations are particularly below 100 to 150 feet above ground or height above average terrain, where you have non-line of sight propagation is more substantial, you get really great results. And there are reviews of people that talk specifically about that. They had a regular kind of technology in their garage or their attic, and it wasn't sufficient. They put this in and then it did better. So no, it's not designed for your 400-foot tower installations with 8 to 12 dBi gain, 15-foot long antennas. No, but for your stations that need that improved performance from the technology, it's great. The Scan 3 is for your scanner radio, very much like the LMR1. Covering, but general coverage of 100 to 1500 megahertz, both mobile and base station. I actually use it in my vehicle. I have a dedicated scanner radio on the Scan 3, and then I have the 2M440 Plus on the other corner. So the summary of the models, which fits you. It depends on the customer. There are different styles of ham radio operators. It's great. Some like to do multiple frequency bands and modes. Some are more focused on maximizing on select bands. It meets the variety. Like I said, the 7.5 inch 2M440 is the least expensive one, $89 from the reseller for the cost conscious ham radio operator. The $10 more, you get the added 220. The 9 inch is a little bit more ultimate performance where it's feasible. LMR1, obviously, we talked about it. Also trucking, taxi, and service companies. I didn't mention that. And then the Scan 3, that's obvious. Okay, so how are these NMO antennas mounted? There's a whole installation page. I put a lot of work into it on my website. It's good reading. Instructions do come with every antenna. Again, at the corner, we talked about that. Listen, when you have an antenna at the corner, oftentimes you would think that you would have directional characteristics. A lot of us, that comes from the CB days or 10-meter days, where the vehicle essentially is pulling the signal in the direction opposite the corner. But when you're doing VHF, UHF, you're using the downward metal as almost like a dipole kind of counterpoise, right? And so you are multiple wavelengths in every direction. So essentially you're still substantially omnidirectional. I wanted to get that out of the way. There's a lot of ways you can mount these antennas. As far as magnet mounts that are very convenient, the flat style tends to work the best. This is a layered one here. There are various manufacturers, as opposed to the ones that peak. The flat style works well. And you know what? They more approximate the through-hole mount, which is really good. A lot of times it's good to have a magnet mount, by the way, before you, whatever antenna you use, before you drill a hole in your vehicle, to check what the approximate match is going to be, before you drill the hole. If it were needed, then move that over there. But there are all kinds of mounts available now. There's the standard inexpensive L bracket mount, if in case, for example, you have an aluminum roof like some F-150s, this is an easy way to do it. There are even adjustable universal style mounts for all these hatchbacks. I've used these before with great success. Here's the magnet mount on a pickup truck. People wonder about mag mount capacitive coupling. If you ever want to look at the formulas, I went through all of them to show you that, a 3-inch mag mount or so, great VHF, UHF, a 5-inch mag mount, even on HF, not moving. I wouldn't. For as low as 7 megahertz, 40 meters. All right, but you can see the exact calculations if you're curious. It's on the installation page. Base station, we've alluded to that a little bit before. This is the key right here. All right. When you have the radios going straight out, okay, you may get a really good SWR on 440, but you don't get as good an SWR, regardless of the antenna style, on 2 meters. On VHF, because you have as low as 25 or even lower resistance component to your LCR. So you'll see some antennas that bring those downwards. Yeah, well, yeah, but then what about 440? Well, 440, you can start disrupting the pattern. So this is not brilliant. This is just, clever use of a, HP network analyzer in a test range and finding the ideal length and positioning and angle in order to optimize your SWR and your pattern performance on VHF, including 220 and UHF, all in one. Again, COMPACtenna is designed to be simple. Not simple-minded, but simple to install. Make it easy. All right. I wanted to make a comment about the microbeam. It's getting more traction. I thought, wouldn't it be nice to develop, a beam that's so small that generally it'll fit right up through the attic, 20-inch by 30-inch, fully assembled or almost entirely fully assembled, and fit into many attics, much less go on a rooftop and look like vent piping, and still give you greater than expected performance, 7 dBi, 10 dB MEG, mean equivalent gain we talked about before. How do you do that? Well, you start with the driven element. See, this is different too, because if you have an antenna that's going to work on 2 meter and 440, then you have 2 different sets of elements for each, and matching, either coaxial matching or otherwise. Here it's all in the feed. See, that's totally different. It's all in the feed, and then taking advantage of the near field dynamics that I talked about before, you can have reduced spacing on the reflector spacing. And then instead of using a dipole, using a full wave loop, well, you actually also decrease the height. Everything's getting smaller essentially, at least in the vertical. And then you gain from the spatial diversity horizontal, and you gain in the gain because of the characteristic of a full wave loop. So you get more performance distinctly out of a micro beam than you would expect. And there's a really nice video by Ham Bandit on YouTube that's his on his house talking about it. HF, close. HF, simple. The 20 meters also work 2 meter and 440, obviously. Well, not necessarily, obviously, but a roughly 20-inch stem, right? Quarter wave, 3/4 wave, roughly. Of course, you do have all that's going on in here that affects it, but it works. So that's the 20 meters. The CB is similar. We talked about it. Shortwave, general coverage reception. Ground plane counterpoise, I talked about that already. You know, this is something, I mean, there are small antennas for backyards. This is tiny. You could even put mulch over this, you know, and I mean, nobody's going to know. They won't even know. This is in the attic. It fits there. This is on the vehicle we talked about. And that's the last slide.
All right, very good. Thank you. Thank you, Dr. Jack.
Thank you. I will stop sharing screen. Thank you for your patience.
Gotta get everything all squared away here. Are there any questions for Dr. Jack?
Looks like
Rob, go ahead.
Hey, thanks for a great presentation. I'll have to find one somewhere and pick it up.
I have
You
one you
talk-
can play with if you like.
Oh, okay. Okay. Well, if you've done it,
I have.
then I'm sold. It'll be nice to have a shorter antenna. You talk about Flutter and those kind of things. That you talk mostly about receive, but how does it affect transmission in a varying environment?
The same way. It's a good question. And in fact, I mentioned Harold Wong out there in LA, who did initially just a really entertaining reception analysis. But then after that, he did a transmission analysis. Gain in reception is gain in transmit, almost always, assuming linearity in both directions. And there are some rare exceptions, even in ionosphere propagation, where you have dielectric kind of characteristics. We won't talk about that right now, but essentially the same thing in a multipath environment. A multipath environment, let's say, has 5 pathways, you know, in reflection, scattering, refraction, diffraction, that makes it to, say, your vehicle in this case. Just pick that example. And there's going to be some cancellations. There's going to be some summations. You know, that's on the reception. On the transmission, you also have multipath environment and multiple pathways that make it back to you know, whoever it is that you're talking to. That's the simple answer.
And is there a preferred source for purchasing?
Oh, I have some really nice resellers. They're all different. They're all unique. Ham Radio Outlet is right there in Los Angeles, the south side, I believe it is. And well, then they have 2 more in California. DX Engineering is out of Ohio and Nevada. They're fantastic. Some really smart people there. HRO has stores all over the place. There's Hardland, a friend from the past who became reacquainted, and he has a radio shop. He repairs tube radios. It's really amazing. It's like going into a museum at his place. He does some work there. And then there's a small one, KB Cubed, out in on the East Coast, that does Hamfest and also online. They just do the tri-band version. They selected that one.
Dr. Jack?
Yes.
I used DX Engineering, and they did a nice pairing with the low height mag mount to go with the COMPACtenna, and so it was a good package deal, and they were fast and good delivery. So
That's where I picked up mine as well, was DX Engineering.
Yeah.
Excellent. The low profile, was it the MFJ or the Pulse Larsen one that they selected?
I'm going to turn this off. It doesn't have a label on it, which is strange, but it was their recommendation to have the provide a compatible one that I understood you had helped to choose or select for them.
Okay, very good. Yeah, just FYI, some of the higher frequency, low profile magnet mounts were developed for the microwave community, everybody. So what they'll have, some of them is a pin, a very, very small diameter pin and a flat disc at the top. Okay, so it's designed to be used that way for below 1 gigahertz, right? VHF, UHF. But for microwave frequency, 2 gig, 3 gig, 4 gig, even 6 gig, some of them are rated. You remove that, all right, and you remove that part of the dielectric then. And then because it's designed for microwave antennas that have a tiny little pin that then goes inside that opening. But if you don't put the pin, the dielectric and the pin, the nylon or whatnot, dielectric and the pin back on it for standard VHF, UHF antennas, whether it's the leaf spring style like you saw mine have, which is like Larson, or the little bigger diameter pin that has a spring in it that goes up and down for VHF, UHF, they may not make contact. Okay, so just keep that in mind. If you get one of those styles, pay attention to that.
Yeah, this is the one that DX Engineering was offering up.
Great. Can I see the top of it? Yes, that may be one there. Can you see with your fingernails if you could actually pull that disc off the top of it?
Yes, it'll come off. Yeah.
Exactly. And you see underneath there, then you also take what would you call it? It's tubular, dielectric out, and then it has a tiny little opening in the center. That won't work then with your standard antennas out there for ham radio. You have to keep that in there. Okay.
But that's compatible with your pad and the
it's an excellent choice.
connector here, so it's a good transition period.
Yes, thank you. You are right.
So you don't have any lumps of the impedance at that point.
Right, should work out real well. Is it looking good for you in terms of matching up?
Yeah. But I was surprised when there were no markings as to the manufacturer or source or anything. But it's well made.
Yeah, it's a good one.
All right, any more questions?
And only one of the antennas does 220?
Yes, the original, the 7.5-inch tri-band.
And I believe David had a question.
If it can be painted.
Oh, I hesitate for a moment because they used to be painted, and the obvious answer was yes. And as long as there's no metallic component, including to the pigment, which is not common nowadays, such as Krylon fusion paint. In this particular case, the answer is still yes. Because now it uses a UV stable black ABS. So the answer would be yes, and something such as Krylon Fusion, which is very, very available from many places, including, well, Sherwin-Williams, Walmart, whatever. Yeah.
All right, very
Do
good.
you ever use anything with aviation for airplanes? In the VHF?
Hams are cool because it comes from such a variety of walks of life and hobbies and whatnot. So there's no question that people have taken it and mounted to for example, to the bottom of the fuselage or the top, or even somebody did it on a helicopter to the landing apparatus, but above, of course, where it lands. So yeah, the fuselage of an aeronautical vehicle can be a very good ground plane, especially because it slopes.
I'm a Tupperware guy, and so I'm building a composite airplane, and I'm wondering how, without there's no metal substrate there unless I actually factor one in for a ground plane. So there's essentially no, I'm limited on that.
Yeah, well, you know, yeah, if you don't have a metal fuselage, then you create a ground plane. If you can use the compact counterpoise on the inside, you know, and then the antenna sticks out on the outside, or if it's composite, the entire antenna could be on the inside, right?
Yes.
You're going to have the properties of the composite in terms of the, you know, it's characteristic on the pattern and the impedance, but not much typically. For most composites, not much.
Thank you.
Yep.
Any more questions? Greg?
Yes, I don't know if I missed it, but for all three antenna types, what are the spec sheets saying what the maximum power is before you burn them up?
Yeah, that's a good question. And I put them through all the rigor years ago without the radome on there, and put amplifiers into them and held the key down and see how long it took before they actually smoked. These are great questions. The bottom line answer is, yeah, the specs are on there. The 7.5-inch antennas, it's 85 watts for your VHF, and your UHF is 50 watts. That's a 50% duty cycle, specifically 1 minute transmit, one minute on key. It will depend a little bit on your, you know, your environmental conditions. All of that has to do with, you know, listen, even a monofiller Tesla coil is going to generate some heat, even though it's a broad film, you know, and it has to dissipate. All right. So that's the answer there. But the LMR1 and the 2M440 Plus has a ceramic dielectric inside, and can take more. I conservatively rated for 100 watts, same duty cycle. Personally, I put much more into it, but that's what it's spec'd at. So the 7.5-inch version are basically rated for pretty much any mobile you have, right? 50 watts, 25 watts, 65 watts, even 80 watts, you know.
Very good. Thank you. Any more questions?
Yes, I have a question.
Yeah.
Dr. Jack, the 20-meter antenna has the same type of less flutter properties as the 2-meter 440?
Yeah, it is built a little differently inside, but it still has a monofiller Tesla-like coil inside, plus a helical component. So it does reduce the dramatic drops that you get from the ionosphere polarization flux, and as well as with the shifts in the angle of signal propagation. And that was shown. That's why I showed that slide that the major defense contractor, you know, showed. You know, that was their real big surprise, that it would reduce that. Now, at the end of the day, again, listen, you know, if you're on a particularly bad sunspot day or propagation day, you know, and the only thing that's going to hear anything is a 3-element HF beam, you know, at 200 feet, you know, and you're going to hear a few things. I don't care what technology, it's not going to do it. But if you're in a reasonable, you know, propagation situation where you have, you know, low to moderate strength, and then some of the signals are low, but they're still there, okay? Yes, it is going to mitigate that as they showed.
Okay, so if I put, for example, what I'm thinking is one of your 20 meters antennas, build a little ground plane, put that on my back patio flat roof, and use it as a receive antenna for my on 20. That's my predominant DX band in the daytime. So I should hear weak signals on that better than I do through my end-fed half-wave antenna.
Well, very possibly, depending on the length of the end-fed half-wave, you know, it may have substantial gain characteristics to it, but especially because it's outside, you're reducing the amount of noise that you're getting from inside your house. So yes, and by the way, it's it's very inexpensive. So, you know, it's to every situation is different, right? So there's no 100% answer to anything. That's why we're hams, you know, we experiment stuff, but you're certainly not outlaying a lot. But theoretically, yes, what you're doing is kind of similar to people that have taken a new approach and they're using such as an NFED or a dipole for the transmit side, but they're using a magnetic loop for the receive side. Now, the problem there is then you have to retune every time to optimize a magnetic loop. You theoretically need to turn it, et cetera, you know, retune. You know, it's not ideal until you start throwing a lot of money into it. But, you know, it has its sense, okay? And then they use preamplifiers on it, you know. Well, this is a much less expensive way to go that approach, Ron. So I think it's a pretty clever idea, and it certainly wouldn't cost you much to do. Definitely a good question. Let me know how that works out for you. Do you use a preamp on your receive side or just whatever is built into the radio?
Just whatever is built in the radio. I was considering a magnetic loop, but now I see this as an idea. And I was going to ask you if a preamp would be necessary, but it sounds like not with your antenna.
Yeah, you know, look at the videos and see what people are doing, putting it up at the park, and within minutes, you know, they're contacting people all over the country. I mean, it works, you know. So that was last month, and we certainly weren't having great, you know, activity. We're still on the rise curve of the propagation cycle.
Right. Thank you very much. Great.
Yeah, thank you.
Thank you, Ron. Just a couple more questions. Midge, go ahead.
First of all, I want to say I'm honored that I was invited to this talk by IVE Harold, who did your one of your tests with your antennas. I live in an HOA, and I've had a $1,000 fine for putting an antenna on my unit. So I am so interested in your stuff, and I will probably purchase all 3 of your antennas.
Oh, Midge, thank you.
I am so happy to meet a genius. I really, to figure out how to do that. So you are a genius. So thank you so much. And I thank Harold as well.
It's God's visions in the morning, but thank you. I then I worked my brain real hard to try to explain what he told me, but okay, go ahead.
All right, thank you. Greg, go ahead.
I have one more crazy one for you, Dr. Jack, and appreciate the presentation.
Oh, thank you.
Have you experimented with when I say the collinear design where it's stackable? Have you tried taking your particular antenna design and work up where you're doing the electromotive and magnetic fields in a more vertical stackable to see if there's any more sensitivity or reduction in the noise floor by doing that?
Yes, but it wasn't. I paused because I want to summate a lot of information into a little answer. The whole design here was to be small, right? But there would be nothing wrong with using, for example, a co-phase harness, right? Or a not just a power divider, but some phasing type of apparatus, signal splitter, to have 2 of them. Say you were using the ground plane counterpoise and you had 2 of them, and you put one above the other, and about a wavelength, by the way, okay, about a wavelength, right? So about 6 feet, one above the other, and then of course you'd want to have a standoff. You know, now that you get into that because of the effect of the tower itself. But theoretically, you could do that, and then you would still benefit from a reduced size. You would increase the gain. You would of course increase the gain. You would tighten the elevation coordinate pattern to some degree, and then you would still have the benefit of something that was reasonably small for a higher gain than would be expected, you certainly could do that. That would be interesting to try. It just wasn't the direction that I pushed, because it was all about small. But you're still small then, right? Because it's not like you're taking two long, fiberglass antennas and stacking them or something like that. Or yeah, you could.
All right, very good. All right, once again, thank you, Dr. Jack.
Thank you. Thank you, everybody. Appreciate all your great questions.
All right, thank you. We have a little bit of housekeeping to do before we conclude this evening.